Welcome to Module 3 of the OrthoEpidemiology series, Power and Sample Size. Last time we decided on data points, and we were going to consider issues of bias that could influence our data. One major issue with data is when there isn't enough of it. Obtaining adequate statistical power is of paramount importance, particularly if the study has a result that fails to reject the null hypothesis. As such, a discussion of power and sample size is warranted prior to considering issues of bias. I think it is easiest to think of power as resolution that you may get from a television set. The higher the resolution, the more pixels there are, and the clearer the picture is to see. Similarly, the more patients there are, the clearer the study results become. More power is usually a good thing, but not always. It is possible to get a statistically significant result that is clinically meaningless. As such, it is important to interpret the results in the framework of a clinically meaningful difference. How many patients are needed are largely determined by the form of your outcome of interest. In general, when using inferential statistics, power analyses are necessary. Inferential statistics means that you are using your sample to make inferences about the larger population the sample came from. There may be other elements needed, but by and large, you will require an estimate of the error you're willing to tolerate, the variance of the population, and the magnitude of difference you wish to detect. Typically, this takes the form of an MCID, or minimally clinically detectable change. The ever-perilous power analysis. Methods of power analysis vary, but essentially keep in mind that you are trying to make inferences about the larger population using your sample. In most cases, you are trying to relate an exposure to an outcome. The more patients you have lets you see the difference in that relationship more clearly. So in general, the number of subjects that will result in adequate power is dependent on four things. Type 1 error rate desired, which is typically 0.05. Type 1 error is the chance of finding a difference when none exists. 2. Type 2 error, or 1 minus type 2 error is power. This error is the chance of finding no difference when one exists. Be careful of studies with small numbers of patients that state conclusively that there are no differences between groups. This study might be underpowered and committing a type 2 error. Delta, or desired difference to detect. Clearly, detecting a 5% difference between groups with any accuracy will be more difficult and require more patients than detecting a 50% difference. Population variance. If a population is more variable, then more patients will be required to detect an average difference. You can increase power or decrease the number of patients you need by increasing the difference you are willing to detect, i.e. wanting to detect larger rather than smaller differences, or by decreasing your population variance by getting a more homogeneous population. However, these will decrease your generalizability or external validity. Most often, the desired difference to detect will be dictated by a clinically detectable change. The first element we are concerned with is error. In a simplified way, we are looking at our alternative versus our null hypotheses. So there are effectively four possibilities. If you have a positive study where you reject the null hypothesis, you can either be correct, in which you have found a true difference, or you will have committed a type 1 error where you find a difference when one does not exist. The threshold for committing this type of an error is usually 5% chance, or a p-value of 0.05. If you have a negative study where you fail to reject the null hypothesis, you can either have a true no difference, you have correctly accepted the null, or you can have a type 2 error where there is a difference but you fail to detect it. The threshold for committing this type of error is typically set at 20%, or a power of 1 minus type 2 error, or 80% power. The third element is the difference you're trying to detect. This is a picture during my residency. The really tall guy in the middle is Stu. If I were to ask you which building is closer to Stu, which would you say? This tan building or the tall building on the right? Clearly, you would say that the tan building is closer to Stu. Now, if I were to ask you which is closer to Stu, this tall building or the tall building next to it, which would you say? It's not so easy to tell, is it? It's like this because the differences are smaller. Differences are harder to see when they're smaller. You need more resolution, or in statistics, you need more power. The fourth element is the variance in the population. For this, we will examine jars of jelly beans and ask which has a greater proportion of red jelly beans, this one or this one. It's not so easy to tell in this case because there's lots of variance in the jelly beans. How about this one or this one? It's easier to see that the jelly bean jar on the right has more red jelly beans because there are less variance, so the differences are easier to see. Consider this example of two populations represented by their confidence intervals as line segments. Example A shows two lines which overlap. The populations look different, but since their confidence intervals overlap, the differences will be non-significant. This may be a true no difference, or it could be a type 2 error. Suppose we increase the sample size as shown in example B. The effect of outlying observations will be muted and confidence intervals will be narrower, potentially resulting in a statistically significant result if one exists. In example C, we cannot make the sample size larger, but there are some observations that are dissimilar from others in demographic ways, like say pediatric patients, or in joint replacement studies, suppose there were a few patients which were much younger or older than the average age. You can take that group out of the population, which will yield a more homogeneous population, but it will decrease your external validity or generalizability. It should be noted at this point that this must be done a priori and not just to engineer a statistically significant result. Doing this would result in selection bias and likely invalidate the entire study. The next module discusses biases such as this. This example is merely to show the effect of decreasing population variance on the power of the study. Example D shows a larger, more homogeneous population, which will result in the ability to detect very small differences. So what does this all mean? Suppose you had a very large sample size and you found a 1 millimeter difference in the KT1000 measurements for anterior drawer of the knee after ACL surgery, with a p-value of less than 0.05. Could you say that it was clinically significant? Maybe, but probably not. We generally power studies to detect clinically meaningful change. The minimally clinically important difference is the smallest change we would consider clinically important. For patient-reported outcomes, there's typically a standard value for this. For the DASH score, the MCID is 12 points. For the Harris Hip score, the MCID is 7 to 10 points. Each instrument has a measure people would consider clinically meaningful. This equation shows a standard power analysis for a t-test of independent samples, where both samples will be the same size. Let's make the math numbers simple in the context of what we just learned. The sigma is the sample standard deviation, or the variance. The z-alpha and z-beta are simply the z-scores found on a table for the thresholds for your type 1 and type 2 error rates, and the delta is your desired difference to detect. We plug all those numbers in and we get 64 patients per group. Simple algebra, but suppose we don't know the MCID, or there isn't one, and a sample variance is not available or reliable. Take estimated blood loss, for example, for pediatric neuromuscular spinal fusions. The published estimated blood loss is all over the place. Which study do you believe and pick variance from? In cases like this, you can use a more standardized method to come up with reasonable sample sizes. It may not fit your data exactly, but the power calculation is based on assumptions. Any power analysis, it should be noted, is based on different assumptions. The black box warning here is that many statisticians do not approve of these methods, but they have come to be accepted now in many orthopedic circles, particularly for observational studies. For randomized trials and higher level studies, we recommend more robust methodology for obtaining appropriate sample size. Now that the disclaimer is out of the way, to obtain a power calculation in a pinch for a variety of applications, you can use the tables in this book and use medium effect size, which ironically gives you 64 patients per group in our previous example. A Cohen's delta of 0.05 for a t-test yields 64 patients per group, and for a one-sided test, 50 patients per group. This is based on a delta of 1/2 a standard deviation of the mean. Jacob Cohen, who was a brilliant statistician, felt that medium effect sizes were ones that could be seen quote-unquote with the naked eye. Another interesting way of saying that is clinical relevance. This study was a systematic review of measurements of health-related quality of life, the conclusions of which were interesting to say the least. They found that in 32 of 38 studies of these measurements of health-related quality of life had an MCID close to 0.05 standard deviations of the mean. As such, it seems reasonable to use this as a basis for power calculation when the MCID is unknown for your primary metric of interest, or if it doesn't have a published MCID. So a common question is, do I need a power analysis? If you're comparing things and trying to use your sample to make inferences about the population, then the answer is likely yes. So level 4 studies which are descriptive likely do not need a power calculation, unless you are looking at before and after treatment results and trying to infer what the results of such a procedure would be on the general population. A final word about power. Many studies in orthopedics are underpowered. Authors should be honest about the limits of their power and of their sample. Being underpowered does not always mean the results are unimportant. It just means that you do not have enough patients to detect a certain effect size. You cannot conclusively accept the null hypothesis with suboptimal power because there is an increased chance of making a type 2 error. A final word about power, I promise. Dichotomous data often requires more patience than continuous data. Calculating multiple tests requires correction and can increase your rate of false positive findings. Fishing expeditions in which there is no primary question are less scientifically appealing for this reason than question-based inquiry. I think it's possible to overpower a study and to obtain statistically significant but clinically meaningless results. Thank you. Please leave questions in the comment section.